All right, so we're going to talk about Lewis dot diagrams. Lewis dot diagrams are useful for visualizing both ionic and covalent bonds, though honestly it's mostly used for the covalent bonds. Here is a representation of an oxygen atom with its 6 valence electrons. Basically, we use dots to represent the electrons. Please note that the valence electrons are paired around that oxygen atom. We have already talked about the fact that you have 1 s orbital and 3 p orbitals. So that is why you see those 2 electrons that are not paired, okay, in 2 different spots, because they would be in 2 different p orbitals. That's the way we fill those. Okay, they're placed in 4 groups, basically 1 group above, 1 group below, 1 group to the left, and 1 group to the right. For ionic bonds, it's a pretty simple idea. Okay, the metals lose their valence electrons, the nonmetals gain. And so what you see on the screen there is we're going to have sodium, our metal, lose its 1 dot, its 1 valence electron. We put it inside brackets. Notice that the bracket, there's no dots inside of that for the metal sodium, and then we have a +1 charge on the outside. Chlorine, on the other hand, gained the 1 valence electron. It now has all 8, so it is satisfying the octet rule. But because it picked up, gained 1 electron, it has a negative charge. So sodium loses, ends up with an empty 3rd shell in this case. Its first 2 shells, of course, are still full. The chlorine gains an electron, leaving it with a full shell. The total charge is 0, and each atom is either empty or full in that last shell where it had electrons. 8 dots for the octet rule. Here's a second example with magnesium. Of course, magnesium has 2 valence electrons, being that it's an alkaline earth metal. It's in column 2. It needs to lose both of those. It gets bonded to 2 chlorines, both chlorines gaining 1 to make it 8. And so you notice that here we have the Mg +2. Okay, it lost both. And then each of those chlorines with a -1 charge, they each gained 1. We don't really do much with the ionic bonding because it's simple. The metal is always going to be empty, and the nonmetal is always going to be full. And that's pretty much it. There are no other variations with this. And so it gets kind of boring after a while. We're going to spend most of our energy talking about covalent bonds, okay, 2 nonmetals. And by the way, you should have noticed on the sheet that we just finished, covalent bonds are for molecules. So covalent bonds are molecular bonds. So anytime you see molecule or you see molecular, think, hey, these are covalent bonds. These are between nonmetals. In this case, each pair in the bond is shared between the 2 atoms. We don't have any ions. The electrons are really not free to move around. They're kind of locked in place between the 2 atoms, forming that bond. In sharing these electrons, the oxygen sees 8 electrons. So if you're thinking in terms of being at the nucleus and looking outward, the oxygen is surrounded by 8 valence electrons. On the other hand, each of the hydrogens, looking again outward from their nuclei, they think they have their 2 valence electrons. Their shell is also full. So either way, everybody thinks it has a full shell. It's just done by sharing instead of giving and taking. Now, how do you know how many valence electrons? Well, we do that by our trend. Column 1, 1, column 2, 2, skip the transition metals, boron 3, carbon 4. nitrogen 5, oxygen 6, fluorine 7, and of course, noble gases have 8. However, there's a second way to look at this, which is how many, shall we say, holes are there to be filled when they want to share a bond with other atoms. Well, hydrogen basically has just one spot, one hole that it can fill up. Column 2 technically has no holes to fill up. These are going to all be metals anyway, and so we cannot, they're not going to be part of covalent bonding. We get over to boron, which can act as a nonmetal at times, and it has 3 spots that it could pair up to form covalent bonds. Carbon actually creates 4 spots. It actually splits apart into 4 different orbitals so that each electron that carbon comes with can bond 4 times. Okay, it's the only column that can do that, and it's one of the reasons that carbon ends up being sort of the backbone of so many things. All our food, all our fuel, all our life forms, all carbon-based. Nitrogen here has 5, but that 5 means there are 3 spots that can be filled, so 3 holes to be filled. Oxygen with its 6 leaves you 2 holes to be filled. Fluorine, all the halogens have 1 spot. Part of the point of paying attention to the holes is it tells you just how many bonds that atom can make. So the halogens and hydrogen can only bond once, okay, because there's only 1 spot to share an electron. Oxygen can bond twice. Nitrogen can bond 3 times. Carbon can bond 4 times. The halogens only once. So here are the rules to make Lewis dot diagrams. First rule, step 1, determine the number of valence electrons. So you look at your compound and you check each element in the compound and use our trend, 1, 2, skip, 3, 4, 5, 6, 7, 8. Sulfur has 6 valence electrons. Oxygen also has 6, but there are 3 oxygens in this compound. So altogether there are 18 valence electrons from the oxygen atoms, plus the 6 from the sulfur. So SO3 would have 24 valence electrons to work with. This is always the first step because you have to use them all. Okay? You can't have any missing. You can't have any left over when your diagram is done. This is all you have to work with, and they have to be done in pairs. Step 2, we have to determine basically what I call the central atom. What atom is going to go in the middle, and the other atoms are going to go around it. Generally speaking, you pick the atom that has the most open connections, the most holes. In other words, it can bond the most times. In this particular case, both oxygen and sulfur have 2 holes. And so there is a second way to decide which one to pick. You pick the element that appears fewer times. This molecule has 1 sulfur and 3 oxygens, so we're going to make it so that the sulfur ends up being in the middle and the oxygens will go around it. So these are generally the 2 rules you use. As I said, most of the time we use part A here. We pick the one that's going to bond more times, the one that has more holes to be filled. Carbon is always going to be in the middle. On the other hand, the halogens and hydrogens are never in the middle because they only bond once. Okay, step 3, we place a single pair of dots for each bond. So for instance, there's 1 bond between the sulfur and an oxygen. There's a second bond. There's a third bond. So that's the first part. We place a single pair of dots for each bond. Second part for step 3, we then place additional pairs. Notice it's always done in pairs. We place additional pairs of dots around the external atoms, as long as you're not talking about hydrogen. Because remember, hydrogen can only have 2 electrons. It's only got 1 shell. And we do so until they get to 8. So here I'm adding pairs of dots. So that oxygen now has its full octet. It has 8. Okay, now we'll go to this one. It has its 8. And finally, the last oxygen, it has its 8. And so now every oxygen, every external atom, not the central one, all the other ones, now have up to 8. Now, the only exception to this rule is if I had run out of dots. Okay, and I can check real quickly how many dots did I use up? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have used up my 24 dots. But let's suppose I had only had 22 dots, 22 valence electrons I was trying to represent. Then that's as many as I can put in. So I'm not going to put 8 around each one if I don't have enough dots to do that. So that's assumed for this step, that you actually have that many. Step 4 says, place the remaining dots around the central atom until it has 8, unless the supply of dots is exhausted. And as we just counted, 2, 4, 6, 8, and so forth, up to 24, we had used all 24 dots. They've all been used up. Here's the deal, though. That sulfur is not surrounded by 8 dots. It does not have a full octet of valence electrons. So it gets us to step 5. And again, with the exception of hydrogen, we check to make sure each atom fulfilled the octet rule. If the central atom, in this case sulfur, has only 6 dots around it, then we need to slide a non-bonded pair to create a double bond. So for instance, I'm going to move those just over a little bit to give me some room, and I'm going to slide those over so that I now have a double bond between this sulfur and the oxygen beside it. Now, does it matter? Could I have picked the one on top or the one to the left? Sure, doesn't matter which oxygen I picked. What matters is I cannot take 2 electrons that are already part of another bond and move them. I have to take ones that are not bonded, and then I can slide them over. Now, as far as we're concerned, okay, this oxygen is still surrounded by 8 dots, even though I moved 2 of them over to the other side, because it still sees 2 above and 2 below, so those 2 orbitals are filled. And then over here, it's sharing 4 of them in a double bond. So that oxygen sees all 8. But now this sulfur also sees 8 because it's sharing these 4, and then it's sharing these other 2 pairs with the other 2 oxygen atoms. I have not added any dots. I did not take away any dots. I simply moved some dots over to create this double bond. So right off the bat, folks, this suggests that doing these things in pin is not a good idea. Because if you get to this point where you decide, oh, I need to move some dots and create a double bond, if you have done it in ink, then it's kind of hard to erase and fix your drawing. If the central atom had only 4 dots around it, then we would have to slide 2 non-bonded pairs and create a triple bond, or we also have the option of creating 2 double bonds. Now, we did not have to in this case because we were not missing 4, but one of the things you can do is you are counting up your dots and you put them around the external atoms. If when you get to kind of this point and you're like, hey, I need 4 more dots to make every one of them have 8, then you know that means I have a triple bond or I have 2 double bonds. Now, how do you know the difference between which to use? It kind of depends on what your options are for the electrons that are not shared so far. Kind of depends on what's involved in the compound. So before I go on, just let me go back real quick through these rules. So first, always the first step, how many valence electrons do we have? Second, we pick what's going to be in the middle, and we just go ahead and put the other ones around it. And notice that our orientation is sort of always in a plus sign orientation. Something's in the middle, we go above, below, left, right. Okay, then we start putting in the bonds. That's our third step. Put pairs of electrons around the external atoms, external meaning not the central one, until each one of them has 8, as long as we do not run out of our dots, as long as we have not used up all our valence electrons. Then we focus on the central atom. If it does not have 8, but we have used up all our dots, then we're going to have to slide 2 of our dots that are not bonded so that we can create, in this case, a double bond. If it turned out we were missing 4 dots, we would have to create a triple bond or 2 double bonds. So, some hints in doing Lewis dot diagrams. First off, if it's a polyatomic ion, has a charge, okay? Negative charges mean add extra dots. So I would look at, in this case, SO4, just like I looked at the SO3 in the previous example, but then my total I would add 2 more to because I have that -2 charge. If I had a positive charge, I would reduce the total number of available dots. In this case, NH4 plus, ammonium ion. That plus, there's no number there, so that's +1. That means I have lost 1 valence electron, so I would reduce the total of available dots by 1. Again, carbon is almost always the central atom. Hydrogen and the halogens are never the central atom. With diatomics, what are diatomics? 2 atoms. When I have just 2 atoms, that's it, just 2 atoms. It really doesn't matter which one you want to call the middle, because there's just a pair of them there. Don't do them in pin, and don't be sloppy. In other words, try to make all your pairs of dots line up, either horizontally or vertically. It makes it much easier to keep straight. What are the bonds, what are not the bonds, and that you have a pair for each one. Don't make any rings. Tend to do linear diagrams. So let's look at a couple of examples here. Okay, C2H6. Step 1, how many dots? Okay, well, how many dots is a carbon going to have? 4. Every carbon will have 4 dots. How many will a hydrogen have? 1. Each hydrogen has 1. So 2 carbons plus the 6 hydrogens going to give me 14 total dots to work with. Okay, now I pick the central atom. Never going to be hydrogen. Okay, carbon's going to be in the middle. So my 2 carbons are going to be in the middle. And I'm going to put my hydrogens around them. So there's my step 2. And again, notice how I've tried to orient things up and down and left and right. Okay, now step 3, put the bonds in. Okay, there's a bond between the 2 carbons. And now we have the bonds between the carbons and the hydrogens. And again, I can do this as long as I don't run out of dots. And I can always check real quick, 2, 4, 6, 8, 10, 12, 14. Okay, didn't run out of dots, and I have all my bonds in. Now, if at this point I check my atoms, hey, those 2 carbons, they're both surrounded by 8 dots. I mean, if you look at any individual carbon and then look around it, it's got 8 dots. If you look at the hydrogens, every one of those hydrogens has 2 dots to one side. It's 1 orbital. This one's done. You've followed the octet rule. Steps 4 and 5 involve the octet rule. This one's finished. Okay, second example. C2H4. Again, step 1, how many dots? Now, last time we had 14. How many are we going to have this time? How many does each carbon have? 4. We got 2 carbons, that's 8. How many is each hydrogen? 1 for each hydrogen. I got 4 hydrogens. Going to have 12 dots this time. Process is still the same. Central atoms, never going to be hydrogen. So the carbons go in the middle, and there's my 4 hydrogens. And now I put in my bonds. Okay. Everything's bonded. A bond between the 2 carbons and a bond with each carbon to the 2 hydrogens, as you see. Okay, now octet rule. The hydrogens are okay. They each have 2. But what about our 2 carbons? Do they have 8? No, they do not have 8. Now, how many dots have I used up? Okay, I had actually only used up, until I brought in that last pair, 2, 4, 6, 8, 10. I'd only used up 10. Okay, now one of them has 8. Okay, but the other one does not. I'm missing 2. If I'm missing 2, means double bond. So I have to slide a pair that is not already bonded. So I can't pick the dots that are already connected to the hydrogens. And I'm going to slide it over and create my double bond. Now, even though it's still just the 12, each carbon is surrounded by 8 dots. True, 4 of them are sort of in one area, one orbital area of it, but altogether, each carbon is surrounded by 8 dots. Each hydrogen has 2 dots. And then a third example, C2H2. Again, how many dots? 10. Central atom, carbon, 2 hydrogens this time. Put the bonds in. Used up 6 dots so far, so I have 4 more to put somewhere. Now I'm not going to do anything more to the hydrogens. They never get more than 2 dots. So, we're going to start doing the fill up for the octets. So there's 2, there's another 2. Okay, one of the carbons has its 8. How many is the other carbon missing? It's missing 4, okay? Everybody but hydrogen's got to have 8 dots when you're done. It's missing 4. So I am going to need a triple bond in this case. Now, by the way, in this particular case, it's easy to know I don't want 2 double bonds because I can't have double bonds with hydrogen. Hydrogen can only bond once, okay? And there's only 2 carbons and 1 bond between them. So this 1 bond is going to end up being a triple bond. And as you might imagine, triple bonds are much stronger than single bonds because they're sharing 6 of them. And as a result, this shape is one that tends to be linear. Actually tends to be fairly line-like. So that is the idea behind doing Lewis dot diagrams. Any questions?